So what we're going to talk about today is details. The emphasis here is software is details. And there's a reason I want to make this emphasis. It's something that I've come to over the years, and it's by observing the way that casually we use language at times. Things that are possibly relevant. There's a book with 97 things in the title. That's part of my kind of bio for the GOTO site. I've contributed or edited 3 books with 97 things in the title. I will actually quote from this one a bit later, but I also have this kind of like notional big picture view, the patterns, the architecture, but that also takes in detail. We're going to see that as we go. Most recently, under lockdown, so something to do, myself and Trisha G finished 97 Things Every Java Programmer Should Know, and we've run a lunchtime book club with GOTO about that, and we're going to do another book club related thing fairly soon. And that a lot of that is about the details. But let's just jump in and kind of start picking up some things here. This is a classic paper that was written 40 years ago by Meir Lehman. Programs, Life Cycles and Laws of Software Evolution. It's worth a read, particularly, I mean, it gives a historical sense, you know, the world as it was perceived in 1980, and whenever we look at the world in a particular year, actually what we're really experiencing is the previous years. So really what Lehman is describing is his perception from the late 70s. And there's a number of great observations, laws, ideas in there. There's a lot that you can mine and you can compare with how the world has changed or has not changed. And I'm going to probably refer to Lehman again later in the talk. But this is my favorite sentence. Can you have a favorite sentence in a talk? Well, or an article? Yes, you can. This paper, my favorite sentence is this one. And I think he had a great deal of fun putting it together. Any program is a model of a model within a theory of a model of an abstraction of some portion of the world or of some universe of discourse. So next time a member of your family says, so tell me, what is it that you do? What does a software developer do? See if you can memorize this quote, because that'll stop them asking you questions, and they probably won't want you to fix their computer after that either. But there's something else here. It's an abstraction. What is an abstraction? An abstraction, it comes from the Latin abstrahere. It basically means to draw off. It's about removal. We use the word abstract a lot. Abstract classes, abstract data types, abstract thinking, layers of abstraction, abstract machines, all of this kind of stuff. We use it extensively, but we're not very good at saying, well, what is it? Abstraction is about the removal of stuff. The problem is that sometimes we get the sense, particularly when we sort of talk about roles like architect and, you know, hand waving. First time I ever asked somebody, what is a technical architect? This was kind of mid 90s. What is it that these technical architects in this organization do? And the guy I was working with, a guy called Mike, said, oh, architects in this company, well, they wave their arms a lot, and they testiculate, which is a fancy English way of saying they talk bollocks while waving their hands. Hopefully I'm talking sense here, but there is an idea that we end up with vagueness. And Dijkstra was really clear on this. The purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise. That's the point. That's a good abstraction. You absolutely nail it. Now, there's a couple of things here, one of which is he used the word semantics, and you may have ended up in a discussion or a conversation where at some point in the conversation, people sort of say, well, hang on, what do we mean by this? And somebody says, oh, that's just semantics. You know, that's a very common dismissal of an argument or a discussion. Oh, it's just semantics. It's like, well, wait a minute, this is software. What do you think it is that we're doing? It's just semantics is another way of saying, oh, don't worry about that. It's just meaning. Well, given that you're probably discussing meaning, this is really important. That is what a software system is. It is a construct of meaning. It is related to people's requirements. It is related to our understanding of the world outside, but also the world of the code, how everything is put together, how frameworks work or don't work as we expect. It's all about meaning. There really is nothing else. So to say, oh, don't worry about it, it's just meaning, is a misunderstanding of what we do in software. you know, when we talk about processes, most of the time what we're doing is a process, a development process is a way of establishing and negotiating meaning. We're trying to find out what we're trying to build and how we're building it. Another dismissal that we get in the same breath is, oh, it's just details. It's a kind of dismissal. Oh, it's just details. It's like, well, hang on. What do you think software is? What is it? What is it separates the code, the act of software development, the cares, the surprises, the bugs? Where do all these come from? They are all details. Now, this is not a new observation. And Peter Weinberger quoted in John Bentley's More Programming Pearls, had just a simple quote: details count. Marissa Meir, formerly of Yahoo, she said, geeks are people who love something so much that all the details matter, to the point of being overwhelmed and yak shaving. But there's that idea. That's what separates various roles. One of the things that we can see in software development, and the people who are most effective at it, it's not to do with mathematical skills. It's often to do with understanding of meaning. We know that linguistics is actually has a stronger correlation with people's ability in programming than maths, for example. But it's also that idea of attention to detail, because we know that you can't just casually throw something together and hope that it works, that the details count. There's no kind of, you know what I mean, kind of wizard that you can enable. I want something that, you know what I mean. Well, no, we don't. Your job is to establish the meaning. But there's something that is also more challenging and more interesting. There's a lovely book by Will Gompertz, Think Like an Artist. And there he makes an observation about creative professions. We're talking about a very specific mindset. When it comes, that's crucial when it comes to the act of creating. It is an attitude that can be encapsulated in a simple but demanding rule. This is what makes it at once obvious and challenging. Always think both big picture and fine detail. That is the challenge, that we are embracing two ends of a spectrum simultaneously. It is not that you do one or the other. And it's not the naive idea that sometimes, oh, let's, you know, if you're in a meeting, a discussion, or you're looking at some development processes, there's the idea of, well, let's just do the big picture and then we will gradually, it's like watching a plane land, we will land this in more detail as the ground gets closer to us. We will see more detail and we will do that progressively over time. Actually, that's not how we work. We constantly go, oh yeah, big picture, customer wants this. Now, hang on, what field is that going to be in the database? Boom, we're straight in there. What does that mean in terms of referential integrity? What does that mean in terms of the code that I'm going to deal with? Am I going to do this in JavaScript or am I going to do this in TypeScript? All of the details matter. So there is this idealization that when we think of software, we think software architecture, we think, oh, that's really big. And somehow software architecture is separate from code. In many people's minds, they separate this. Always my question is, what did you think the software was made of? Where do you think it comes from? This is one of those kind of like difficult conversations you have to have. Where do babies come from? Well, where does software come from? It kind of comes from the code. What were you making things from? In the same way that building architecture has to care about physics, normally you don't have to care. So I've got this nice mug that I picked up from, there we go, disappeared, from CERN last year. I did a visit to CERN. You don't need to know particle physics to do building architecture, but you do need to respect materials science, that aspect of physics. Otherwise, you're going to be in for a very big surprise. This stuff matters. We know that it matters in the physical world, but we know that it matters even more in the software world, or we should know. We have a habit of saying, oh, it's just implementation. Those are implementation details. But what is implementation? It makes it sound mechanical. It's like we're hammering something out. And it's like, yeah, it's kind of an interesting metaphor. But it turns out that what we're talking about is design. All of this code is design. It's an expression of design. What we sometimes dismiss as an implementation detail, one person's implementation detail, it's just like, oh, that's too small to worry about, is another person's design domain. If you're writing web apps, you probably don't give a second thought to device drivers. But how would your world look if you had no device drivers? Your world would look very isolated and very dark. You need those device drivers. They might be just details from where you're standing. It's a long way down. On the other hand, if you're a device driver writer, web apps, that's just like a trivial idea. I mean, it's not important, it's not interesting. It's just a thing that somebody builds on top of the most important thing, which is the device driver stuff, the lower layers. Wherever you are, somebody else's main work, somebody else's business is a detail. That's a matter of perspective. But when we flatten it all out, we realize these are all at the same level of detail and intensity. So when we're talking about minor implementation things, actually, these are design decisions, and they have a habit of surprising us. So let's talk about architecture. So there's a nice quote from Grady Booch, which helps us understand architecture. Architecture doesn't have a unique definition. You know, what I mean by that is there's no single point of origin where the first person used the term software architecture and we can trace it all back, and therefore we can say, oh, what we're saying here is consistent with software architecture, or that is not software architecture. We can't do that. There's lots of different ways that people approach software architecture. Some definitions, though, are more or less useful than others. And for me, when people talk about architecture as the marketecture, the PowerPoint diagrams, the big boxes, I'm not going to say that that's not architecture or that that does not capture some aspect of architecture, but it's very, very simple. It's often the big boxes aren't the thing that are interesting. And we are seduced by the kind of physical presence. When I draw a big box on a diagram and I draw a little arrow, the little arrow is little and the big box is big. So clearly the big box is more important. That's just a visual thing. But what we need is a better way of appreciating this, because these are not physical things like buildings. That's where the metaphor breaks down. So Booch's definition I find appealing. He talks about architecture representing the significant design decisions that shape a system. The decision that shape a system. What do we mean by shape? By shape, we mean this is what your work is going to look like. This is what is going to happen over the next few months and few years. This is where the money's going to go. This is where your effort is going to go. That's what architecture is. It tells you where your work is. It tells you how to organize your work. That's not trivial. But what do we mean by significant? Well, it's not scale in an ordinary sense. It's not size of thing, although honestly, some code bases are just ridiculously large, but that's a negative in that sense. They should be smaller. What we need is a better measure. It's effort, it's time. How much effort would it take to change that decision? And that's not a box decision. Sometimes that's about the relationships, and sometimes it's about the things we can't see, the details. So that's a really important one, because a lot of what actually constitutes the significant design decisions, we don't know in advance. We only discover their significance over time. But it also tells us that when people say, oh, it's not about the code, they have the marketecture view. It's about the big stuff. Well, maybe it is big. It's just little, and it's repeated lots. A small thing that is repeated everywhere starts to define the very physics of your program. Let's go back to physics and CERN, okay? Those are only small things. Electrons, the lepton family as a whole, protons, neutrons, quarks, these are all small things, but repeated lots, it gives you a whole universe. I'll leave out the dark matter and dark energy. That's a separate conversation. But that's the point. A small detail, repeated lots, is not a small detail. It becomes big, it becomes significant. That's how we create technical debt. That's why code quality is an integral part and not separate from the concept of software architecture. I've had software architects say, oh, well, that's just a coding issue. Code quality is just a coding issue. No, it's the very fabric and existence of your structure. And this idea about understanding the relationship between the big picture and the little picture is an interesting one. So I've got a nice picture of Paris here, and honestly, I would love to leave the country and go to Paris. This is a good time of year to go. Everybody talks about Paris in the spring, but actually I quite like it in September. So this is as close as I'm going to get, Google Maps. It kind of lacks the feel of Paris, but let's just go with it. Now I've got a nice big picture here. Let's just ask a very simple question. From this is a big picture. What can you see? What you can see is very significant stuff that's been marked out for you. Roads, significant roads. If I want to travel, these are obvious. Also marked out for me some of the sites, the Eiffel Tower, the Arc de Triomphe, catacombs. I can see the green spaces, the Bois de Boulogne. I can see the river. I can see all of this stuff. This is great. What about the direction of driving? Can you see that on this map? No, you can't. You cannot tell. And importantly, although we might know which side of the road France tends to drive on, Parisians have a slightly different relationship with driving, but also a lot of Paris is one way, particularly in the center. So there's a point here. Can you tell that at this level? No. Well, let's zoom in. We're now at the level that you can easily use this as a walking map, and yet I still can't tell what the driving direction is. I have to go in really close. And at this point, we start seeing little arrows. And at this point, we can establish that kind of on the whole, in this part of the world, they drive on the right, kind of, because there's lots of exceptions to this rule. And we can see that here. Now, for a lot of people, these are just details. But I want you to consider if somebody said, you know, we're going to change the direction of driving. Is that a small detail? Is driving the side of the road you're driving on, is that just a left or right thing? Is that just a small detail? No, the last country to do this in Europe was Sweden. That was 1967. It was a huge effort. It was massively expensive at a level that no country could probably do now because the car is much more entrenched. Now, the point here is that it's not visible on the big diagram, yet to change it is hugely expensive. Do we have a parallel in software? Well, yes, we do. In software architecture, this is a common question that I get. It's the execution architecture. How are you structuring the flow of control in your system? And I've had people tell me, people that I would otherwise, normally, have good experience and have got some really good thoughts on other aspects of software development, who told me, oh, threading, oh, that's just an implementation detail. Oh, you get that from the library. You just kind of, it's a small detail. We don't have to worry about it. Really? Threading tells you how. Threading, or your choice of execution architecture, interrupt-driven, time-triggered event systems, all of these things, that describes the fabric of your universe. It is the laws of physics of how your code runs. It's not a small detail. To try and change it is a huge, huge cost. So this is something that is invisible but everywhere and doesn't appear on people's diagrams. It's a detail that actually matters and is defining. It's an inversion. It's not a small detail. It's one of the most important things that you can ever answer the question to with respect to a component or a whole system. But there's also the other stuff that's hard to change, but we consider to be a detail. Identifier names, spelling. Yeah. So there's a lot of people who are very familiar with this word. Okay. This is a Java interface. If you're watching from the .NET world, hi. Here we go. Same spelling, just with an I in front. Cloneable, very strong statement there. Now, there's an interesting thing about this, is that this spelling was used in 1995, and it was adopted by Microsoft. In as much as there is any logic to English spelling, and sometimes people say, well, English doesn't really, the problem with English spelling is it's not logical. That's a misunderstanding. English spelling does not lack logic. It has about 6 or 7 different kinds of logic simultaneously in the same language. That's the difficulty. It's not the absence, it's the excess. There are lots of multiple systems that are competing with one another. And in as much as there is any system to those systems, this is how you spell clonable. And so you will notice that there is a missing letter, that E before the A. It shouldn't be there. And you can go to Wiktionary. There you go. It's not a common English word, but guess what, people? Yes, you as a software developer have been part of a profession that has managed to change the spelling because everybody copied the Java thing. There was actually a note in the original release, if I recall correctly, that said, we really need to change the spelling of this before too many people use it. Too late. Architecture is not about the things really that are big. Architecture is about the things that there are big dependencies on. That's a subtle inversion of where people are coming in from. It's not about the boxes, it's about the arrows. And so therefore, if those details are repeated and you are depending on them, then suddenly it's a big deal. Names matter. There's not an, remember, semantics matter. This is what we do. We build stuff out of meaning. Now, I live in Bristol, and over the bridge, we've got 2 bridges across the Severn that go to Wales. The first city on the other side of that is Newport. How new do you think Newport is? It's a few hundred years old. I don't think it's very new at all. How much would it cost to change the name Newport? Well, everybody knows it as Newport. In the UK, everybody knows it as Newport. That's what it is. All the signs in Newport are about Newport. To change the name is not a simple global substitution. It's not a simple rename refactoring. The point there is that it is to do with the dependencies. It would take years and a lot of concerted effort. So these are non-trivial. There's lots of other little details where people talk about the bits and the bytes we don't need to matter. And one of my favorite examples is windows.h, not because I think windows.h as a header file in C is a good example of how to structure code, but it has a lot of history. Here is a header file for an operating environment and system that is around 35 years old and has experienced 16, 32, and 64-bit and multiple hardware platforms. And it has had to evolve and experience all of the pain. And shifting between the bit sizes is not trivial. There are decisions to be made when we move to 64-bit. Do we use this representation or this representation? That affects the way that the C code and the portability of code goes. But for most people, the decision about, oh, it's just a 32-bit or 64, we don't need to worry about that. It's just a detail. If you're Microsoft, it's not just a detail. It's actually your business. It defines the work of whole teams in trying to maintain compatibility and make these decisions. For the Linux community, so this is the representation choice taken by Windows, the Linux community tends to take this choice. So this is more common in the Linux Unix space. But those decisions are not trivial. They define people's work. They also define whether or not old software works in new environments. These are not just minor details. They are enabling. They are the physics of your system. So this is the thing. Architecture is not just the big picture. It's all the details, but we need to learn about them. We don't always know them in advance. So Tom Gilb's quote on this, I think it's really quite good. Architecture is a hypothesis that needs to be proven by implementation and measurement. You need to build it and then you need to watch it. You need to have a great idea. We need to have a terrible idea and refine it. But the idea is you need to have some ideas. And some of those might not work out. That's the whole point. Don't consider architecture to be an artifact, a fixed artifact. It's a hypothesis. You need to be continually experimenting. And that's where you start learning that that thing you thought was just a detail is actually utterly dominant. So Sarah, interesting font. I believe it's Rockwell. I quite like fonts. Yeah, I do use a few fonts. But yeah, this is Rockwell. So let's talk about that idea of learning, because this idea is that we don't know which details are the ones that are significant. One of my other interests outside the world of software is fiction, writing fiction. I tend to write short form fiction, flash fiction, very short. I have not felt as inspired this year due to the pandemic, but I've done a little bit of writing. But I've also written blog articles, and I've always been surprised by where they go. You start with one idea and you end up somewhere else. Even with a blog article, technical article, how hard could that be? Well, turns out often you end up somewhere else. And there's an interesting guidance or an interesting observation in this book by Robert McKee, Story, where he's talking about plotting, particularly plotting for films. But there's a lovely observation. He says, if a plot works out exactly as you first planned, you're not working loosely enough to give room to your imagination and instincts. I think this is a really important insight, this idea of the looseness, the idea that if everything does work out as planned, perhaps that's a little disappointing, because perhaps, well, what did we learn? Well, we learned that we were right. Okay, but one of the reasons people engage in creative activities is because they have incomplete knowledge. They want to see where things go. And there's that idea that perhaps something better could come along, but you only realize that as you get in the detail. As you were in the meeting or at the whiteboard or whatever, you thought you understood it. Now you start building it, you realize you didn't understand it perhaps the way you could do. And as you start building it further, you understand that your previous assumptions are actually no longer valid. So there's a word, I run a page on Facebook, WordFriday, where occasionally, I've not done it much recently, but I always put language and linguistics related stuff up there in the meantime. But on Fridays, I sometimes will showcase an unusual word. And the word I think that applies here is pantser. An unusual word, quite literally a writer who writes by the seat of their pants, in contrast to a plotter. A pantser doesn't have, doesn't work to have an outline. And I think it was Louis L'Amour, an American author, who once said that when his daughter was little, she once asked him, "Daddy, why are you typing so fast?" And he said, "Because I want to find out what happens," which I think is this lovely way of looking at it, that we don't yet know. Until we hit the detail, we don't really know what the software is going to do. We have vague ideas, we have desires. We perhaps big them up a little bit and reframe our desires as requirements. That sounds more technical, but they are desires and wishes and half-formed thoughts. The other half needs to be elaborated by creating a thing. A customer needs to see what the thing actually looks like. You need to observe and monitor at runtime to see what the thing actually does and how people are actually using it, as opposed to how we thought we were using it. We need to actually build the code to really understand that that brilliant thing that we had an idea for is actually in practice a terrible architecture and it's not maintainable. That's what we need to do. It's all in the detail. So there's lovely commit strip. If you're not following commit strip, I do strongly recommend it. I have the book from the commit strip guys. And there's this lovely one that captures this. Project manager talking to a developer. Someday we won't even need coders anymore. We'll be able to just write the specification and the program will write itself. Oh, wow, you're right. We'll be able to write a comprehensive and precise spec and bam, we won't need programmers anymore. And do you know the industry term for a project specification that is comprehensive and precise enough to generate a program? No, code. It's called code. That is what it is. It is not manufacturing. It is not implementation. It is design. The activity of creating something at that level of detail is an attempt to formalize something. It is an attempt to truly understand it. We might have a partial understanding, but let's acknowledge that for what it is, partial. And we will find details that surprise us, the details that can't be dismissed. Performance turns out to be something we care about. Now, unfortunately, the problem is when it comes to performance and optimization, when people don't care, they often roll out the quote from Tom Knuth, "Premature optimization is the root of all evil," or at least most of it in programming. And sometimes people will generalize this the wrong way. Optimization is the root of, no, he was very specific. It's about understanding the time. This tells you that a software development process must be a time-based process. It must be a process of discovery. Sometimes we don't have the right questions for which we need the answers. Only time will give that, and only when we hit the right level of detail. And when we talk about details, people often think, oh, you know what? I don't need to worry about a sorting algorithm because that's just a small detail. And you know what? Most of the time, people are right. They don't need to. But every now and then, you do need to. And actually, there's an interesting point here, because when you ask many people about the performance characteristics, and I get this a lot with web developers and actually native application developers, that there's often a sense when you say, oh, what are the performance requirements? Oh, we don't have any performance requirements. That is there is a very simple way to discover that you have performance requirements. And let's just look at it here. I'm going to use the kind of like everybody's kind of like favorite lab rat. Everybody's favorite kind of lab rat, which is the kind of like the sorting algorithm is computer science is kind of like fruit fly. I'm just going to pick up an observation from Kel. I always get suspicious when all my unit tests work the first time. I must have missed something. In 97 Things Every Java Programmer Should Know, Marit van Dijk has a lovely piece on unit testing. And one of the quotes that I've lifted from that a lot and used a lot recently in my workshops and my training is, never trust a unit test that you haven't seen fail. I like that way of looking at it. You know, it's always on green. Do we know that there's even a circuit that turns it to red? I would be suspicious with a physical device that only ever showed me one status. So there's an interesting insight there. But here we're going to look at something else. I'm going to say, I'm doing this in Python. I'm going to say, I'm just going to use the built-in sorted algorithm, and I'm going to assert that the result is sorted. And I'm going to define is sorted like this. Okay, and it's a simple piece of Python to confirm that the result of sorting something is indeed sorted. I'll leave aside the other aspects, that it should also contain the same members as the original sequence, but let's just work with this. What I want to focus on is performance. The stuff that you are likely to get from any self-respecting library has this kind of performance. The stuff that people normally write first time or get taught at the beginning of an algorithms course normally has this kind of performance, bubble sort or exchange sort. And there's a big difference between these two, and you really start noticing the difference when you've got a million items. And this is the point. Suddenly you care about something that you previously didn't care about if somebody uses the wrong thing. This is the biggest way to discover that somebody has performance requirements. If somebody says, I have no performance requirements, give them something that's so hideously slow or has such a terrible response time, you know, put like a sleep 10 seconds in the middle of a loop, your main loop, people will suddenly discover they have performance requirements. Somewhere between where we didn't care and this, we started caring an awful lot. And that boundary, might be a soft boundary, is your requirement. You have learnt that details do matter. Okay, now we're going to do something slightly crazy. I'm going to go for permutation sort. This algorithm simply goes through all of the possible combinations. If I give you a sequence of numbers, it goes through all the possible permutations until we find the first one that is sorted. It has absolutely shocking performance. It's absolutely terrible. At this point, people discover, oh, you know what? I do care. Then we have one of the great sorting algorithms of all time, BOGO sort. Let's just randomly sort it and see if it's, you know, while it's not sorted, just shuffle and just see what we get. This has a slightly different performance. Now, we must also be very careful to not distract ourselves by metrics and oversimplistic thinking. The wrong kind of abstraction. Sometimes we focus on one detail to the expense of another. If we start looking at one of my favorite sorting algorithms, it was first introduced to me pretty soon after it was invented. It's probably the only good thing to ever come out of 4chan. It's about 2011. And I've tidied up the code. The code on 4chan is a bit messy. You can do this in just straight Bourne shell. This is a thing called sleep sort. And it has a number of interesting properties. So it turns out that it will sort by using delay. And this has the rather interesting property that it has a linear time. So there is a point here that normally we don't consider algorithms to be the most important thing. And yet we say they're a detail, and yet Google is a company that was founded on one algorithm. For most people, we might say, yes, actually, it's not as important as you think it is. It is commodified in the library. But in some cases, it changes everything. I remember doing a training course for a company. It's about 15 years ago. It was on C++. And simply, this company did a lot of design work, CAD work, chip design. Almost all of their key work was done in Perl. I'll leave aside my own personal opinions about how I feel about Perl at various times. But one of the reasons that they shifted to C++ is actually there was an algorithmic complexity they couldn't control in Perl that meant they needed to control the algorithms more tightly. And it was causing them performance headaches. The point there is that they didn't just change their algorithms, they changed their programming language. They changed the investment and the substrate of what their code was. When people say, oh, it's just a programming language decision, that's a huge decision. You know, there's a lot of differences across these. But there's also the blind spots that we have and how we depend on things, the little details. So we go back 4 years. 2020 as a year sucks, and 2016 honestly really was a pretty crappy year as well. Although I'm going to say 2020 is worse. 2016 was the low point up until that point. But one thing that passed was the left pad incident. The left pad incident was the discovery that many sites transitively depended on a small piece of code, just a few lines long, that was trivial. All it did was pad out a string in a particular way, you know, zero padding or space padding. That's just a detail, surely. Well, it turns out that lots of people had a direct or indirect dependency on this code and did not know that they had a dependency on this code. And then that code was pulled from NPM, and a lot of websites went down, suffered errors, and so on. So the point there is that a lot of people just sort of, oh, I need to pad a string. And this is it's not unique to JavaScript culture, but there's a lot in JavaScript where people say, oh, I'll just take on another dependency. Honestly, you know, you need to watch out. You need to manage your dependencies. Every dependency is a vulnerability, okay, or it's a scope for vulnerability. Every dependency offers an opportunity for, increases your attack surface area. Every dependency is, as I said, it's a risk, it's an exposure, it's a possibility for surprise and a possibility for assumption. Now, I'm not saying you should copy and paste everything in, and certainly people shouldn't have been dynamically looking at this. But when we look at the code, we realize actually the code wasn't that great anyway. This is not a great piece of JavaScript, and we should always thank people for their generous contribution to open source. But that doesn't mean that it's good. Their acts are good, the code may not be good. And when it was pulled, somebody else quickly substituted an alternative version that is actually worse from a coding point of view. This is really not very good code, and it's filled with misunderstandings about how JavaScript performance works. Now, I'm not a JavaScript programmer, but I had a go at this, and I ended up with just a few lines of code. And we've had tests mentioned in the chat, and right before the thing to test, and they will fail. So I wrote some tests. I wrote my own mini JavaScript testing framework. I wrote some very trivial tests, just reality checking tests, where I named the constraint or the property that I wanted, and I had a simple action that I wanted to confirm. This is not the most rigorous set of tests. The testing framework actually fits on one slide in a generous font. And this is what happens when you ran it against my code. Everything's green. And then I ran it against the previous two versions. And this was the big surprise for me. This was not what I expected. The previous two versions actually fail. They don't actually do what they're supposed to. There are well-defined cases where exactly the wrong padding occurs. This was a revelation. Again, watch out for the stuff that's out there on the internet. Don't arbitrarily take on these things because there are assumptions. Your dependencies are not just a set of physical things. Parnas observed, connections between modules are the assumptions which the modules make about each other. Many developers have a very narrow view of dependencies. They think this class uses this class, that's a dependency. Yeah, that's true. But you also depend on your platform, your programming language version. Your programming language version, if you are coupled to it, may prevent you from actually migrating. So there's still code out there that's Python 2. Python 2 is kind of no longer a thing. It's Python 3 is where you're at. Why are you on Python 2? Why are you not migrating? Oh, it'll take work. Oh, that's significant. Oh, we're using a particular library that hasn't migrated to Python 3. Ah, so your choice of another dependency has actually prevented you from developing your software. In other words, dependencies should not be treated lightly, and they are filled with assumptions. People often think, oh, here's my code, here's the world of my code, and normally you think actually about the code you're working on. But here's the obvious dependencies, the code that's in your system. Your IDE will quite happily point this one out. And then there's the code that you don't own. What do you really know about it? What degree of control? And if somebody withdrew it or changed it, what would happen to you? How much control do you have over that? What are your contingencies for that? Do you truly understand your dependencies? I raised this to somebody the other day, and they said, oh, well, do you mean we should understand everything that all of our dependencies own? I said, yes, because otherwise you don't understand your software, because you are basically saying, honestly, it works by magic and hope. These are the details you need to care about, because these are the details that will surprise you. We're not interested in things that don't surprise us. It's the stuff that does surprise us. And that's not normally the big boxes. It's the bits that are subtle and hidden. Sometimes they are everywhere, but we don't even see them. Your platform, your choice of programming language, all of these things. And indeed, the world outside, these are your dependencies. If something changes in governance, that can have a huge effect. Now, we've been focusing on this kind of question of failures. And one of my favorite areas of exploring this is it's a paper I came across a few years ago. It was published 6 years ago. And if you want to bring details out, then expose them, find your assumptions. And we don't do that. I mean, it's very hard to find an assumption, but I always like this one from the Yuan paper, 2014. It's a nice paper in the sense of its title tells you everything you need to know. Does everything it says on the tin. Simple testing can prevent most critical failures. An analysis of production failures in distributed data intensive systems. This is great. So there's a whole load of stuff there. Now, around 2016, which I said wasn't a great year, one of the highlights of the year was going to be October, if I remember correctly. The ExoMars, European Space Agency's ExoMars mission had arrived at Mars and was going to drop the Schiaparelli probe to the surface. Mars is a planet known for eating probes. And things did not go as planned. Schiaparelli's internal measurement unit went about its business of calculating the lander's rotation rate. For some reason, the IMU calculated a saturation maximum period that persisted for 1 second longer than what would normally be expected at this stage. The IMU sent this bogus information to the craft's navigation system. It calculated a negative altitude. Now, one of the nice things I really like from European Space Agency, they always publish their reports, and they did this back in 95 when they lost the 96 when they lost the Ariane 5 launcher. And I love the euphemistic language of space travel. It's an anomaly. This thing crashed into the surface. It's an anomaly. It's such a wonderful, understated piece of English. So feel free to use that next time your whole architecture just the runtime just crashes in a horrible mess of log files. It's an anomaly. And this is again because of the error in the estimated attitude that occurred at parachute inflation. The GNC software projected the RDA range measurements with an erroneous off vertical angle and deduced a negative altitude. Cosinus of angles greater than 90 degrees are negative. So what's going on here? It turns out the spaceships wobble as they enter an atmosphere. Entering an atmosphere is quite a traumatic experience. It wobbles a bit. And what had actually happened is that instead of resetting the variable, oh, I've wobbled a bit this way, wobbled a bit that way, I've wobbled a bit this way, and then when you wobble the other way, you accumulate how much you wobbled. So, you know, I've wobbled half a degree clockwise, half a degree counterclockwise, should mean 0, but actually it ended up with half a degree plus half a degree, 1 degree. It accumulated. So it eventually believed that the aircraft, the spacecraft was kind of upside down. Oops. And this lovely statement, it says, we're taking the cosine of how far off the vertical you are. And there's a simple mathematical truth here. There is an assumption. And this is the point. It's an assumption that the cosine will always be non-negative. Actually, there's a real assumption here. The assumption is that you have a bit off vertical that leads to this. The thing we have to learn about assumptions is they are often bound to details. I made this observation that epistemologically speaking, assumptions are the barefoot trodden Lego bricks in the dark of knowledge. You don't know they're there until you know they're there. You don't know there's a Lego brick there until you step on it with your bare foot. At that point, you are deeply aware of the Lego brick. You have something equivalent to an assumption. You cannot simply internally introspect and say, what are our assumptions? We don't know enough. Assumptions are discovered when they are contradicted. When somebody shows you something, or they show you a customer email, they show you a bug, or they show you something and you go, oh, I had assumed that. At that moment, you have discovered something that you assumed. It was always there, but you couldn't recognize it for what it was. And that's a basic concept of time. That's why we need time in our process to reveal our assumptions. We can formalize it like this. Okay, that's what's really going on, but we probably wouldn't even think about it because it's an assumption, it's invisible. If you want to update the language, given when then, by the way, is just precondition, trigger, postcondition. We've known this since the 1960s. But when we transform it into code, it becomes really obvious. What happens when it isn't that case? Well, that could never happen. And so this is what happened. The fateful miscalculation set off a cascade of despair. Again, another beautiful piece of English that I encourage you to use in your work environment when things go horribly wrong. Oh, that anomaly, that's one way of putting it. The other one is, oh, there was a cascade of despair. Lovely way of capturing it. Triggering the premature release of the parachute in the back shell, a brief firing braking thrusters. Basically, the probe says negative altitude. Oh my goodness, I'm on the ground and I'm fully dressed. I need to get rid of all this stuff and become a grounded probe. Unfortunately, it was 3,700 meters above the ground. Mars's gravity is lower than Earth's, but it's still enough there. And what we see here is another assumption. Almost all catastrophic failures are the result of incorrect handling of non-fatal errors, the blind spot. We focus on the happy day scenarios. The other thing that I found a revelation in this, the majority of the production failures can be reproduced by a unit test. 3/4 in the systems they looked at, systems not designed with TDD or anything in mind, had this property. So when we start looking at all of these things, we start realizing the importance of things like context, the subtlety that even when things appear to be initially working, that we need to appreciate the larger context, that will reveal where the details matter. We have a real blind spot. So Neal Ford had this lovely piece, Testing is the Engineering Rigor of Software Development. I'll do another spaceflight example, and that brings us nicely to the end. 2017, a launch of a number of satellites failed. 19 satellites was due to be launched from Vostochny. And the thing about this to understand is that Russia launches it has 3 sites it launches from, and its most common one, where typically the astronauts, the cosmonauts will fly from, Baikonur, is actually not in Russia. It's not in the Russian Federation, it's in Kazakhstan. That dates back to the Soviet era. But they decided to move the launch to Vostochny, which is far, far, far in the east of the Russian Federation. You know, it's like 12 time zones away. And that is, so they decided to change this. Now, what happened? What they discovered is that all the hardware worked. Everything did exactly as it was supposed to. There's only one problem. Almost unbelievably, the flight control system on the Fregat did not have the correct settings for the mission originating from the new launch site in Vostochny, as opposed to routine launches from Baikonur and Plesetsk. It was launching from the wrong place. Everybody had changed. They'd said, we're going to launch this from Baikonur. No, let's update it, move it to Vostochny. They changed the basic launch sequence, but the upper stages had not been updated. And so therefore, what happens is when we hit the upper stage, the software kicks in and goes, okay, where are we? Oh man, we are halfway around the world from where we should be. And then it fires all its fuel to correct that. It was seen re-entering the Earth's atmosphere around Iceland by a British Airways flight. It ran out of fuel at that point. This is configuration. And configuration has a really important property. A lot of people, oh, that's just a detail. It's configuration. That's not really code. No, configuration is code. I made this point the other day on Twitter, and somebody said, no, configuration is not code. Any language that doesn't have, I didn't engage because the person was wrong and clearly likes being wrong. Configuration is code. If it changes the behavior, it's written in a formal notation and it changes the behavior of your software. Where I come from, we call that code. It's a huge blind spot. Again, a paper, we discover that a ridiculous percentage of systems have latent configuration errors. Okay, many of today's mature, widely used software, we see it in code. People don't check the configuration. They don't test with variations of it. It's assumed to be somehow not part of what we're doing. It's a detail. So I'm going to close here by this observation from Robert Pirsig, Zen and the Art of Motorcycle Maintenance. He makes this observation, it's about motorcycle maintenance and it's about Zen. It's a lovely book. Normally screws are so cheap and small and simple you think of them as unimportant. But now as your quality awareness becomes stronger, you realize that this one individual particular screw is neither cheap nor small nor unimportant. In other words, it's jammed somewhere. Right now, this screw is worth exactly the selling price of the whole motorcycle because the motorcycle is actually valueless until you get the screw out. With this reevaluation of the screw comes a willingness to expand your knowledge of it. And I hope that we can see there are more than a few parallels here with how we can think and should think about software, which is just details. Thank you very much.